Session 3, Trigonometry. What we're going to do is we're going to just recap some of the basic functions and the basic relationships of trig. And then we're going to go into identities, okay? Prove this, simplify this, etc., etc. And we're going to kind of try and evolve some basic recipes to follow. In some cases, the start of proving them, there's very basic things that we do. But then as we move on, there's a situation where you have to have a bit of insight into it. But don't worry, we'll get to those in a bit. What is trigonometry, essentially? Trigonometry, from our previous understanding, is the ratio of the lengths of right-angled triangles. The ratios of the lengths give us a property of an angle called sine, cos, and tan. Okay? So, where are we? Let's have a look. Let's just do a little bit of revision on some of these topics, shall we? Let's have a look. Okay, let's just call this bit just revision. Okay, and we just sit back and we can make some notes as we go through. So first of all, if I draw a little, if I try and draw a circle as best as I can, that's not too bad, but could be better. Yeah, do you know what? Let's just leave it as it is. And let's put in our little thingy out here with an R, and you can see we've got an X coordinate there, and we've got a Y coordinate there, and we know that R is equal to, or little r, my bad, let me just do it as it should be done. Little r, doesn't help to work with an eraser, little r is equal to the square root of x squared plus y squared. Basically, that's Pythagoras because it's 90 degrees. X squared plus y squared equals r squared. Okay, straightforward, and that was the angle theta is in there, correct? We then had that this is quadrant 1, quadrant 2, quadrant 3, and quadrant 4, and we also had the mnemonic ASTC, or cast, whichever way you prefer to remember it. So therefore, lastly, okay, but not leastly, we had the situation of this, where we said that the sine of theta, the cosine of theta, and the tan of theta are all equal to and expressed as opposite over hypotenuse, adjacent over hypotenuse. I know we're recapping, relax. Okay, adjacent over, opposite over adjacent. Okay, just thinking a little bit ahead, is opposite over adjacent. All right. Then, essentially, those are given. Those are the ratios, aren't they? But now, the next side of it is to say, well, what happens if we had a, let's just change to a blue pen and move it back down a little bit. What happens if it was over here, all right? R doesn't change. It's the radius of a circle, okay? And remember, a length is positive. The coordinate can be a negative, okay? So, if we go here, okay, that point is y, this is minus x. So the coordinate of that point are minus x and y, which means that in each case, when we do this, we're going to have what you could look at as a negative length. It's the length on the x, or the y if it was down over here. Remember, if you had it over there, you would have negative x and negative y. The coordinates there, minus x minus y, down in that. So the sign, okay, S-I-G-N, of the function is going to depend on which quadrant you're in, isn't it? That is where we said all ASTC, all are positive, sine positive, cosine, tan and cosine are positive as we follow those around. Now, let's get back to our revision. Then we heard something called identities. Identities over there. An identity was, we proved that sine squared of theta plus cos squared of theta is equal to 1. Just to recap, if you ever asked how to do it, take an acute angle, and what you do is you say, right, let that be whatever you like, x, y, r, or opposite, adjacent, and hypotenuse. You know, I mean, you don't have to stick to x, y, and r. You're proving something, so you can let that be what you like. technically you could say let that be 3, 4, and 5 if you wanted to. And what you'd say, because you know that's a right angle triangle, isn't it? 3, 4, and 5. So you say if that's 3, 4, and that's 5, essentially you'd be giving that coordinates 3 and 4. All right. And then you'd say, right, the sine is opposite over hypotenuse. You'd say opposite over hypotenuse all squared plus adjacent over hypotenuse, all squared. Okay. Let me just put that out of its misery. Like that, you'd square them, add them, and eventually you're going to get 1. I'm not going to go over that. We've done it before. If you want to, please do go for it. Okay. And we also found that sine of theta divided by cos of theta is equal to tan of theta. Those are acceptable proved identities. You can use them at any time. All right. The last thing, well, the element of this piece of revision here is this, right? What have we got? We know the next thing, we said sec of theta is equal to 1 over, and cosec of theta is equal to 1 over, and cotan of theta is equal to 1 over. We know that is tan. How do I work that out? It's the opposite. Okay, cos, sec, cos, okay, of theta, sine of theta, and tan of theta. Now, if you ever see sec, cosec, and cot change to these functions straight away, okay? We don't work with sec, in fact, so much so that your calculator doesn't even have cosec, sec, and cotan on it, okay? You don't need it because you can just change it to sine, cos, and tan. So what we've got is we've got those basic functions that we are going to use, okay? Now, let us continue. Now, if you remember, we did some basic trig equations in the sessions in the previous year. Let's just go over very quickly this. Let us say, for example, they give us this as an example. Remember, we're revising, okay? We're just quickly running through some of the basics before we move on. This is going to be, let's say we are given 13 cos theta plus 5 equals 0, and I'm highlighting that in a box, theta is less than, 0, theta less than equal to 180 degrees. And, and they say solve for argument's sake, they say to us, solve for, okay, find cos theta, okay, or find, let's say they say, find, okay, sine theta plus cos theta multiplied by tan theta, or something. They ask us to find something, okay? The first thing to remember is that we have got here two pieces of information separated by an and sign. That immediately says what? It says draw a graph, draw a diagram, okay? In some of the question papers I've seen, they say, using a diagram, explain this, right? Remember, this might not be numbers. It could be a T. I'm going to do one of those, I think, later on. So we say, right, we're going to draw it. First of all, I always like to say ASTC. And now I go and I say, right. First, step one is isolate trig function. Isolate the trig function. So I say 13 cos theta plus 5 is equal to 0. Okay. I want just cos theta is equal to minus 5 over 13. Isolate the trig function. You're going to see this in trig equations as well. We're going to do the same thing. Isolate the trig, the trig function on its own. Remember when we did surd equations, we did this as well, didn't we? You isolate the surd and then square the other side or cube it to get rid of the surd. Then you took the you rearrange the terms, right? So over here, it's kind of the same process we're going to be. So we say cos theta is that. Step 2 is draw it. Draw that. So we've now got an expression that says cos is minus 5 over 13. Okay? So cos is negative. Where is cos negative? Well, cos is negative there, and put 2 ticks and show as ticks. Where, let me just make that a little bit tidier. Oops. Where can theta be? In other words, where is theta negative? Okay, I'm going to highlight the sign over here. I'm going to just put it in red. Right? So negative means it can be here or there, correct? Because down here it's going to be positive there and cos is positive there. So we found, now we take the second piece of information. Okay. Step 1, step 2, step 3. Take second piece of info and draw it. In other words, put on diagram as a tick. They have said to us in this case, the angle theta is between 0 and 180, which means, I'm going to now do this piece here, between 0, which means it's there or there, right? The last thing I now say, number 4 is show angle theta is, let's rather change that, make it better. It is in quadrant with 2 tick marks, right? So it's where both pieces of information actually agree with each other. That's all we're doing. We're putting them there, we're making both pieces of information agree with each other. Okay, so then we go, so right, now then, I'm now going to draw my diagram theta. So theta must be somewhere up there, right? Theta is up there. The last is I put in coordinates. Okay. Quadrant 5, draw theta and show the lengths from the trig function. Okay. So I can now put in, I know that sine cos of theta is 5 over 13. And I know cosine is what? Cosine is adjacent over hypotenuse, which ties because it's minus 5 over plus 13. So this is now correct. Okay. Can you see the pattern? Okay. So I've got that. Then next, number 6, make sure I've got my black pen. Number 6 is find length of other side using Pythagoras. Use the length of the other side using Pythagoras. In this case that we're busy one over here, you would take it out and you'd say 13 squared minus 25, okay, is 144, square root, and I get a 12. So what are the coordinates of this point up here? The coordinates are actually 5 minus and 12 plus. There's the coordinates, isn't it? Okay. Those are the coordinates of that point. Okay. Remember, they could have given us the coordinates of the point, right? And said, now do it with that. Same process, right? If you've got the coordinates of the point, you can immediately plot it. You don't have to go through the whole process of finding which quadrants it's in. All right? 6, apply Pythagoras, done. And then question 7, okay. use lengths to solve what we are asked. In this case, I think I said, well, let's not think. Let's go and have a look. Find sine theta plus cos theta tan theta. So we would say sine theta plus cos theta times tan theta. You'd say sine theta, in this case, is going to be opposite over hypotenuse, 12 over 13, plus cos theta, which is minus 5 over 13, times tan theta, minus 5 over 12. Okay, like that, right? And you'd multiply those out and you'd just add and subtract, okay, and get an answer. Most of these answers actually cancel out quite nicely, and you get quite a nice number at the end. Okay. Now, that's kind of like, and we did a little bit of proving of identities, didn't we? Okay. Some basic ones. Let's have a look. Okay. What have we got? These are identities now. Identities. Okay. And basically we're going to be proving these guys. All right. Essentially, what have we got? We've got a trig expression here, right? And they say prove it's equal to some other trig expression over here. Okay? Or it could be a number. Prove something's equal to minus 3 or something, okay? Well, first of all, let's just, as I say, we're going to try and put a basic recipe together. Look for number 1, okay? I am going to call this left-hand side and right-hand side. Number 1, okay, start with left-hand side, okay? And put down your expression over there for the left-hand side. Okie dokes. Now, when that is done, all right, we start with that, and we are going to, in essence, simplify this trig expression. Okay, that's what we're doing. We're going to simplify this trig expression over there. Okay, so let's put some pointers down in blue. Let's put down some pointers, okay? What are the pointers? Number 1, if you see tan x, okay, you always change it to sine x over cos x. I say usually, but you could, for example, have tan squared x minus tan x equals something. Okay, you could factorize that, right? So usually it's sine x, and usually this is if tan x is alone. Okay, if tan x is alone, we usually do that. Question section 2. Remember, okay, that you could have, we're going to factorize. Okay, can you see this is the same, very similar to steps to simplifying algebraic expressions, right? Where we went through, look for the highest common factor. That still applies here. Look for the highest common factor, okay? So factorize, we're going to use the same steps. Highest common factor, okay? What did we have as number 2? Number 2 was difference of 2 squares. Remember? Number 3, okay? Not reason. Quadratic, right? Number 4 was cubics. Not really here. Okay, we don't generally see that in this section. Question 5 is grouping. Okay, remember those from algebra? It's the same. We're going to do the same because we're going to try and factorize. Now, in this process of factorizing, remember, okay, very often you're going to see especially number 1, 2, and 3. But bear in mind, I'm going to actually put this in red. sine squared x plus cos squared x is equal to 1. This is an identity, often referred to as the square identity. Right? Often referred to as the square identity. Okay? Now please remember, this I can change to sine squared x is equal to 1 minus cos squared x. But that I can factorize more. That's the difference of two squares. 1 plus cos x, and very often mine cos x, 1 minus cos x. Okay? No, you cannot factorize sine squared plus cos squared into no. Why not? Because it's difference of two squares. Difference means minus sign. Okay? But that I can, and similarly, cos squared x is equal to 1 minus sine squared x. I can do that's 1 plus sine x, 1 minus sine x. Guys, very important that you remember those, okay? Not remember that, but you know sine squared plus cos squared equals 1. Just remember you can rearrange it. You please don't remember this. Try and remember it, okay? You don't need to. Just remember that sine squared plus cos squared, take it to the other side and then factorize, okay? And then, therefore, basically our sort of training should kick in that we look for difference of two squares, okay? Then number 4, or rather I've got two different numbers here going here. Pointers 1, 2, 3 was that one, okay? The next one is going to be then factorize and then cancel obviously out. Okay, 5. Let me put in simplify. Oops, come on. Simplify. In other words, everyone's favorite, cross, cancel, stuff. Yay. It's what we all want to do, isn't it? Because that makes it simpler, doesn't it? That's what this is about. Okay, we've got that. Now there is one more little trick that we're going to have in here, is something called the conjugate. Okay? What on earth am I talking about? Well, I'm going to show you an example now, all right, using the conjugate. Those of you who do AP, when we do complex numbers, imaginary numbers, remember the complex conjugate that we multiply through by to change the, to in essence remove the imaginary number, correct? So, what have we got here? The conjugate, yes, I'm going to say example. They say prove that 1 minus cos x is over sine x is equal to sine x over 1 plus cos x. Okay? Don't worry why we're doing this. Okay? Just it's a thought process. That's all it is. Okay? It's the same as algebra. What were we doing there? We were doing this to simplify. We're doing the same thing here. There's just a bit of a step in between that says prove it's equal to that. But we are simplifying. Okay? Let's think of it like that. Okay? Right. Oh, I said take left-hand side. Write down left-hand side equals 1 minus cos x over sine x. Okay. What did I say the next step? Okay. Look for tan x. Write it as, no tan x. Difference of two squares. In other words, factorize. No. There's no factors. There's nothing. So in other words, this alone cannot simplify. So I can't actually factorize. So I can put on here cannot factorize. Okay? Oh dear. What now? Well, in our little recipe book, we've got something called the conjugate. Okay? So therefore, we're going to have to, all else fails, use the conjugate. What is it? The conjugate of A plus B is, and this is going to be such a revelation, isn't it? A minus B. Why? You should recognize that there is actually the result of the difference of two squares. So the conjugate is the other party of the square, because that puts me back to a squared minus b squared. It's kind of completing the square, but not. Okay? So how do I find the conjugate? I say 1 minus cos x. Okay? 1 minus, that's terrible. Okay? 1 minus cos x over sine x. So I use the conjugate and we multiply by it. What is the conjugate? Well, the conjugate is 1 plus cos x over 1 plus cos x. Okay? I know that sometimes it's referred to as the magic 1 or whatever, because I'm not doing anything different. Because 1 plus cos x over 1 plus cos x is 1. All right? We are multiplying it by 1. We're not changing anything. We're just making a subtle rearrangement. Okay? So what happens there? On top, what do I get? I get 1 plus cos x minus cos x, 1 minus cos squared x over sine x, 1 plus cos x, correct? Now let's take this the next step. Now, 1 minus cos squared is equal to sine squared x over sine x, 1 plus cos x, which is equal to, remember, where's my green, there we go. There we go. And it leaves us on top with sine x, correct? The net result is I get left with sine x over 1 plus cos x, okay? So we've used the conjugate, and once we've used the conjugate, you go back to square one, okay? You're going to then go back to square one. So when you've used the conjugate, all right, you use the conjugate, okay? Let's just put in here, okay, in blue, we say times by conjugate, okay? Multiply through by the conjugate, then go to step one again. All right? In other words, we go right back to the top and we say, right, do we have tan x that's coming? No. Factorize, common factors, difference of, etc., etc. So the conjugate puts us in a space where we actually go back to square one. Okay? It actually gives us something to work with, right? Kidoki. Now, okay, we've got that character. Okay, now we're going to just carry on and do examples in the next section, right? We're going to do examples, a couple of them, about three examples. Then we're going to do reduction formula. So we're just going to keep plowing through trig, okay? Thanks for watching this. I hope that we did the introduction okay, and we've looked at just the processes we're going to follow from now on for factorizing. Cheers. Have a great one. Bye.